Aloha, this is Roger Brewer with John Peard in the Hawaii Department of Health. This is the fourth in a series of 4 webinars on the use of decision unit multi-increment sampling methods to improve site investigation reliability for contaminated soil and sediment. The first webinar, John discussed the importance of systematic planning, especially the importance of spending more time up front understanding the site that you need to investigate before you go out and start collecting samples. In particular, is reviews of historical data, public records for the site, but also visiting the site is very critical. And if possible, interviewing people who used to work there and getting an idea of where there might be suspect areas of contamination. In the second webinar, then I went over more details of decision units and how to designate decision units at sites. This isn't really a big difference from what we've always been doing in the past. Anytime we go to a site, we typically try to identify suspect areas of contamination, and then from a risk assessment standpoint, we might try to focus on potential exposure areas and designate those areas for characterization. The big difference under MIS DU approaches is in the field you physically draw a line around those areas, and then you're going to collect a single multi-increment sample from each one of those decision unit areas and make decisions based on that. It's really critical as part of this DU designation to get it right the first time, so that you want to set your decision units up so that you're comfortable making decisions on the data that come back without having to go back and resample the individual decision units or split them up into smaller and smaller decision units. Sometimes you have to do that. You might get surprised with really large decision units that you thought would be clean. They come up contaminated, but you want to avoid that as possible. In the third webinar, then I discussed the concept of sampling theory. Pointed out that sampling theory is pretty unknown in the environmental industry. It's very widely used in other industries like agriculture, mining, and such. But it's really a new concept, a new idea for a lot of the environmental industry. So it really focused on the limitations of discrete sampling data and how if you collect samples side by side, you can get radically different numbers in laboratories. Testing different pinches or spoonfuls, aliquots from individual samples can be radically different. So in the end, the data that you get from a laboratory isn't reliably representative of the sample you sent. The sample you collected really isn't reliably representative of the area that you collected it from. So that's the first thing to remember in looking into this approach. And before you move on to DU-MIS approaches, is just understanding the limitations of discrete sample data. We also discussed limitations of discrete sample data even in risk assessments, where you don't really know the field precision of a single set of discrete samples collected from a target exposure areas. We demonstrated through our field research you can go back to the same area, collect another set of discrete samples, and come up with a radically different mean or even 95th percent UCL. So these were discussed in detail in the DU characterization webinar. Today, we're moving on to the last final webinar, field implementation of DU-MIS methods. This will be presented again by John Peard, and it really gets into the nitty-gritty details of how to collect samples in the field, how to designate DUs, and avoid the need for multiple remobilizations. So with that, I'll pass it on to John.
Hello and welcome. This is John, and as Roger just mentioned, I will be discussing the field implementation issues in today's Decision Unit Multi-Increment Sampling, or DU-MIS webinar. In our online technical guidance manual, aspects of field collection of DU-MIS samples are covered in Section 5, with specific subsections addressing collection of surface soil samples, subsurface soil samples, collecting samples from stockpiles, collecting samples for VOC analyses, sediment sampling, as well as other field prep and documentation details. I also want to acknowledge up front all the good work of environmental consultants working on DU-MIS investigations in Hawaii over the last 8 years, who have helped to put in practice and refine the field techniques that will be discussed. Field experience is key to learning and understanding decision units and multi-increment sampling investigation approaches. And as we have stressed in earlier webinars, initial planning and preparation are very important in designing and implementing good DU-MIS investigations. After gathering any documented historical information pertinent to the site, we start work with a reconnaissance visit to the site to walk the site and review in the field any important historical maps, photos, or other information we have gathered. We also discuss and sketch the location, size, and depth of DUs that will be selected, and idea any site obstacles that may need to be cleared for access to soil to the site in the DUs. We also note any special safety and health considerations that may need to be addressed, and importantly, test soil sampling tools we plan to utilize for sample collection. This is to make sure they will work efficiently during the site investigation. Also, in our case, when we are doing initial site discovery on historic sites we suspect may be contaminated, securing site access agreements with the landowners to schedule site visits can sometimes be very time-consuming and must be coordinated well in advance of any site visits. Here's a list of some typical equipment utilized for surface soil sample collection for non-volatile contaminants using DU-MIS procedures. Site clearing tools, anywhere from a hand sickle or scythe to heavy-duty weed eaters or mechanical brush cutters, can be critical on some sites, as the sampler needs to have general access to the soil throughout the entire DU for the collection of systematic random soil sampling locations. Also, notice the variety of tools included on the list that could be used for collecting soil. This is to cover any soil density or soil type or condition that may be encountered in one or more of the DUs in the investigation site. Bringing a variety of tools to address any situation that may be encountered helps to get the job done without the need for additional mobilization to the site. With some experience and the right tools, DU-MIS samples can be collected in a reasonable time frame, approximately 30 to 60 minutes per DU, though this assumes the site is clear enough to navigate, soil is accessible, and you have pre-planned and located the DUs in the field. Typically, the biggest factor affecting sampling efficiency is the tool selected or available for sampling and how fast each increment can be correctly and consistently collected with that tool. Depth of soil collected in a surface soil DU is dependent on the investigation data quality objectives. This could be as shallow as 0 to 2 inches if the focus is on, say, what a child may currently be ingesting from soil exposure during play in their backyard, but more typically investigations of surface soils in Hawaii have targeted the 0 to 4 inch or 0 to 6 inch depth interval. I noted earlier the importance of an initial site reconnaissance visit, during which a number of site features can be assessed and subsequently addressed that have the potential to slow down your soil sampling event. Such things as illustrated here: vegetation, various obstacles like equipment, broken down vehicles, etc., pavement that's encountered, rocks, etc. Even with good advanced site review, unexpected events may arise that need to be managed to keep things on track. In our case, that has often ended up to be animal control in the more rural areas: dogs, pigs, horses, and perhaps curious neighbors. Hopefully the DUs you select will be clear to locate systematic random increments throughout and access the soil for sampling. If not, some clearing of dense brush or other obstructions may be necessary, or you may have to break or drill asphalt or concrete pads to access the soil beneath if those areas are to be included in your contaminants average for that DU. Obviously, close coordination with and/or help from the landowner is generally necessary for significant clearing operations. Remember that the representative average contaminant concentration determined from collecting a multi-increment sample in a DU can only be inferred across that entire DU if all areas in that DU are accessible to locate the systematic random sampling increments. Any portion of a DU that is not accessible because of say, a concrete asphalt pad, building, or a significant patch of dense vegetation is a data gap area that would then need to be addressed in the site investigation decision making. Oftentimes we deal with these with some sort of institutional control. We may assume it is contaminated under a building if we find contamination up to the side of it, or there could be other contaminants below the building. So we've got to note that in the site investigation, perhaps put in institutional controls in a final decision-making document, noting that these areas could not be sampled at the time. Assuming that a thorough Phase 1 environmental site assessment or historical review of property being investigated has been completed, and an initial site reconnaissance visit has been completed, proposed DU locations can be designated and drawn on aerial maps of the site before the sampling takes place. These can then be confirmed and adjusted as necessary during the sampling event. As shown here, for exposure area and source area DUs for a former sugar mill site, we typically use Google Earth images imported into PowerPoint to designate the location and dimensions of proposed DUs for the site, and include planned increment numbers and spacing to utilize for each of the DUs. Planning ahead on DU selection and dimensions saves lots of time and effort in the field. Remember, the goal is to locate source and/or exposure area DUs to gather adequate and representative site data to compare to applicable action levels, as well as avoid having to sample yet again for characterization or remediation if possible. To lay out the planned DUs at the site, we typically designate the corners with wire flags and record GPS locations for these DU corners as necessary. In some cases, you may have land survey data or physical measurements to fix landmarks to locate the DUs for mapping purposes. We do not take GPS locations for each of the 30 to 100 increment locations within a DU, as the target increment spacing and systematic random approach is identified and described in the sampling and analytical plan. If you desire more documentation of specific increment locations within the DU, you can place wire flags at each increment and then take a photo. But we do not require such documentation in our guidance. This slide illustrates location of triplicate samples collected in one decision unit. True field replicates are required for all site investigations on a minimum of 10% of the site DUs. More field replicates could be required if the DUs have different target contaminants, soil types, or other significant variables across the site. If less than 10 DUs are designated on a site, then at least one field triplicate sample is required. In this example, the yellow X's mark the primary sample and the green and purple X's mark the replicate samples collected, and there'll be more on selecting replicate locations coming soon. Here's an example of increment locations illustrated with wire flags in a small spill area DU next to a former transformer pad. The goal is to have the desired number of systematic random increments located approximately equidistant throughout the decision unit. There are a number of ways of determining approximate increment spacing for each DU, including working it out in the field with measuring tapes and adjusting and readjusting wire flags, as we first started out with. Over time, though, we learned to save time by estimating the planned increment spacing ahead of time and thereby keep any adjustments needed in the field to a minimum. This is an increment spacing estimation table in our TGM using the formula given below the table. However, it is not unusual to encounter situations in the field where the boundaries of DUs are irregular, which may require some additional field time to determine the best increment spacing to get complete coverage and to document these adjustments. The illustrations on the left side of this slide illustrate the goal to locate increments in a systematic, random manner so that they are approximately evenly spaced throughout the DU in all locations. The illustrations on the right, which includes a simple random and a stratified random spacing approach, generally result in poorer reproducibility if the DU is sampled again than systematic random spacing. Using systematic random sampling, you select a random starting location and then sample at determined fixed spacing intervals across the entire DU. For very narrow DUs, such as along canals or drainage ditches, an alternate zigzag spacing approach may be needed as illustrated. In the field, we may locate these points by stretching a long measuring tape down the middle of the ditch with highly visible clips attached at the increment spacing distance, then use that as a guide when zigzagging down the DU. Some may be familiar with the VSP, or Visual Sampling Plan program, available online from the U.S. Department of Energy. And you may want to utilize this program as another option to estimate and designate increment locations within DUs. With this program, you can import GIS files of DU shapes, select from two grid options, input your target number of increments, and VSP will generate and illustrate potential increment spacing designs, and you can select the optimal increment spacing for your decision unit. Here's an example of increment spacing estimation using the VSP tool in both narrow and square-shaped DUs. Using VSP may be especially useful for irregular-shaped DUs where the increment spacing is not as easily estimated as for square or rectangular DUs. Field replicate samples, typically triplicates, are selected at separate systematic random increment locations across the same decision unit. So these are true field replicates, not co-located samples immediately adjacent to the primary sample collected, as have been used with discrete sampling. These slides illustrate several approaches to selecting systematic random replicate sampling locations. On the left, the approach taken is to take a duplicate and triplicate sample from midway between the increment locations for the initial or primary sample in both directions. So if the round circles are your primary samples, the replicates are chosen midway, systematically midway between the primary sample and midway in the other direction between the primary samples for your replicates. On the right, the DU has been separated into a grid pattern with the total number of grids equal to the number of increments targeted to be collected. So that would be anywhere from 30 to 100 increments or grids for the DU. Within each of those grids, the three replicate samples are distributed in a triangular pattern equidistant from each other within that grid. Triplicate samples are typically collected all at once when moving across the DU, with special care to keep each different replicate sample in their respectively labeled sample containers, usually a bucket or a bag, as illustrated in the lower right here. We have found that using long measuring tapes are very useful for expediting collection of increments at the designated increment spacing in a decision unit. This reduces the number of flags needing to be placed at measured intervals in the DU. We use wire flags just to mark the DU corners and then opposite sides of the DU where increment rows will be placed. A long measuring tape with colored clips placed at the designated increment spacing is stretched between the flags in a row to identify where each increment will be collected. So here are some colored clips. These can be placed, if this is your measuring tape along the first row here, there'd be these colored clips located at the predetermined set increment interval, spacing interval, along that tape. And then once you've gone through and collect your increments at all these marked locations along the tape, you have someone grab this end of the tape and someone grab that end of the tape, and both move simultaneously over to here and place it in this row location, and then those same marked locations are utilized in this row to collect that. And then once this row is completed, you move the tape over to the next row and collect increments at that same interval along that row. So, and you would do that until all the increments in the decision unit have been collected. Again, we found this speed things up rather than marking each location with flags across the whole decision unit. Okay, now I'm going to run through a variety of field tools that have been employed in site investigations here in Hawaii to collect multi-increment samples. Some key points to remember about sampling tools in general, though. First, we are always trying to collect core-shaped increments to get a correct cross-section sample through the entire selected depth of the DU. A core shape is illustrated here. So with a core shape, you're collecting all the particles through the entire depth of the decision unit, whether this be 0 to 2 inches or 0 to 6 inches or what have you. All those particles throughout the depth are captured, equal chance of capture throughout the depth of the DU. If you're using something other than a core, say some sort of spade or scoop, you might end up collecting more of a V-shaped increment, which is actually representing more of the particles at the top of your increment than it is at the bottom. And those particles might be differently contaminated than those, so you'd be not collecting a correct sample or not getting a good reproducible sample of contaminant level for that increment. The sample coring device has to be large enough to collect a good size increment, typically 30 to 50 grams for a 0 to 4 inch or 0 to 6 inch depth increment, using say a 0.75 to 1.25 inch diameter core. However, if the core diameter is too large, then the total mass of the increments collected in each DU may exceed the capacity of the lab to process, at least using standard processing procedures and their typical processing fee. Generally, labs want the samples to be under 2 kilograms, but this may vary depending on the lab. Very large samples could require field subsampling, which adds significantly to the field effort. Another point is to always expect the unexpected and take a variety of sampling tools in the field so you can ensure you get the job done, even if very dense, rocky soils are encountered. Test tools out on initial site reconnaissance, if at all possible, as I noted earlier. And it goes without saying, a superior tool for collecting correct increment cores will always save you time and labor. A simple agricultural TREER coring devices, which has one side open that you can use to put a tool like a screwdriver in and pull out the core. Works great in soft soils. It's really fast. You can grab your increment, put it in your sample container, punch out the increment collected through the open side of the core, and move on. In some soft soils, you may even be able to collect as deep as a 0 to 12 inch core and then split that in half to determine if contaminant levels decrease with depth, especially if the analysis shows that the targeted 0 to 6 inch depth shows contamination over applicable action levels. You'll then want to look to see if the lower depths are contaminated above your action level as well. For surface soil samples, each increment from a given DU MIS sample are placed together in the sample container, typically a bucket or heavy-duty plastic bag. The sample coring device does not need to be cleaned between each increment collected within a DU, but must be cleaned between use in separate DUs. Here's what a typical bulk MIS sample looks like. As we mentioned earlier, typically anywhere from between 1 to 3 kilograms. But be aware that some labs will not take bulk multi-increment samples for processing, at least at a regular processing fee, that are more than 1.5 or 2 kilograms. So check with the lab you are using. If samples are too large for the lab to accept, you will need to representatively subsample in the field, or perhaps pay the lab a special fee to subsample or process the large sample. This is an example of someone sieving and representatively subsampling in the field to reduce mass of the samples to send to the lab. This should be avoided through good planning and tool selection if possible. Doing this work in the field just adds additional sources of potential error in the sampling processing. I should also mention that whenever you're conducting subsampling in the field, reducing the mass of the sample, you'll also want to collect additional replicates of the subsampling process to demonstrate that your subsampling procedures of the bulk sample are representative of the entire bulk sample. So in this case, on the right-hand side, you'll see different stratified random increments are being selected out of the spread out sample here to reduce the mass. So for a replicate sample, you would go back in and collect the sample the stratified random increments at different locations throughout that sample to create the replicate and send that in for analysis. You'd expect that those two samples then would have similar concentrations if your subsampling replicates were representative. Here's an example of other coring tools that are available. There are quite a variety out there. This one was developed by the Army Corps of Engineers and used heavily on military ranges. These have a core-shaped increment on the bottom of them, and it's nice because they have a bar on the top you can just step on, so it helps ensure that once you get that secure into the ground, you've got the similar depth increments at every interval. It says in the slide here that you can go up to 4 to 6 inches deep. I've only seen these with collecting tips that are up to 4 inches deep. So you might want to check that if you're attempting to collect up to 6-inch intervals. But the models I've seen have included different size coring tips so that you could choose different diameters for your cores to collect. And it's got a plunger, a metal plunger that will poke out the sample after it's collected, which is convenient. Here's an example of a cordless drill with an auger bit utilized to bring up samples out of a core shape onto a plate at the surface to collect your increments. This can be a fast and enticing method to use in the field compared to more laborious tools to use, but I would caution you to be sure and test them out. You want to make sure that the volume, the mass of soil bringing up in each increment is approximately equal to what you would get out of a push coring device. So when we're wanting to use this cordless drill method, I usually also bring along a core, compare the volume or mass of soils coming out of these core using both tools to make sure that you're getting good recovery with the drill. In some soils it just doesn't work that well, and you won't get much recovery or recovery that you might expect out of a core. So you want to test that. If it works, it's a nice technique and can be fast and easy on the back. In the illustration there, we've simply taken paper plates and cut a 1-inch hole in the plate and put the drill down through the hole in the paper plate, and then as you drill down to a designated depth, it's bringing up the sample out of that drill core on its veins up onto the paper plate. Then that's tossed in your sample container, in this case the bucket there on the left. Slide hammers are also common to see for soil core collection, which enables you to hammer the core down to a greater depth, especially if you're trying to get down to a 12-inch deep increment depth, which oftentimes people do, so they have the flexibility to look at both the 0 to 6 and 6 to 12-inch intervals in the case that the surface interval, the topmost interval, is contaminated above your action limits. So it takes a little labor, but they're useful, very portable in the field, and widely used. Another variation of this I've seen and have liked to use on some sites is instead of the slide hammer sliding up and down, there's a fixed hammerhead on top of the coring device, and you just pound on the head with a small sledgehammer and pound that down to the depth you're attempting to reach. This slide illustrates other hand tools that may have to be resorted to in really dense, hard-packed, gravelly soils. We encounter these kind of soils all the time in Hawaii, unfortunately. All these years we've been busting a lot of rocks, and a lot of these former commercial sites, these old sugar mill sites, etc., pesticide mixing sites where it had gravel spaced on them, heavy trucks traveling over them for many years. So the soil in these areas are densely packed, have a lot of gravel or their rock in the soils, and you literally need a pick to bust into the soil. So typically they're used blunt instruments they use to create a hole down into the soil to the depth of interest, and then we actually collect the increment. Remember, we always want to try to collect a core shape, so once we get a hole busted in there with the blunt tool, then we can go in on the sidewall of the open hole and collect a core shaped increment with smaller tools. The bottom breaker bar may be a good option if you need to bust asphalt or deteriorated asphalt to access the soil beneath. And here are illustrated a variety of powered electric or cordless spade or chisel bits that do the same thing, get you into really dense, hard-packed soil so you can then collect an increment from the sidewall of the hole you've created. Here's an example of a more remote site where we're bringing out a portable generator to operate the drills, a chisel bit, so that we can drill holes. Again, this is a former pesticide mixing area where the soil is densely packed. We couldn't get into it with a push core or a slide hammer, so I had to use these more heavy-duty tools to get into the ground, and then collect a core-shaped tool up the side of the hole that's busted in the best we can. And here, this slide illustrates what we're trying to accomplish once you get a hole using a powered or hand blunt instrument. You've got your hole busted out to the depth interval interested, and then you take another tool, a smaller tool, to try to collect a core shape increment down the sidewall of that open hole there. This is a lot of work, so you know, it's just the way it is on many sites. If you don't have access to some fancy drill rig, you just got to pound them out. Stockpiles present a sampling challenge due to the lack of access to soil within the middle of the pile. Remember, the sampler must have equal access to collect stratified random increments in the entire DU, both laterally and vertically, to provide a representative sample for the entire DU. So if you come across a stockpile and sample just the top of the surface, even if it's all over the top of the surface, you're only representing what's in the surface, and something very different might be present in the middle of the pile or at the base of the pile that you're not accessing. So the most common approach we've seen used here is to actually just spread the stockpile out, spread it out, flatten it out, so that you can then access the entire depth of the stockpile, or the now flattened stockpile, with a coring device. And then you'd place your systematic random increments throughout that flattened pile, and collect your increments down through the depth of the stockpile. You could also, another method that has been used is to actually move the stockpile from one location to the other utilizing a front loader or some other operation, and then incrementally take samples out of each bucket as it's being transferred from one location to the other to form your 50 increment, multi-increment sample, if you were. Of course, you'll have to calculate the approximate number of buckets and how many increments you'll take out of each bucket to determine or plan out your increment collection for those DUs. But that putting the material in movement allows you to access it and sample it that way as well. In some cases, especially where there's limited space, the stockpile is sampled in small portions that can be accessed, like a truck full, and a decision is made for that portion. Then the next portion is sampled, and so on. Pits and trenches can be approached with the use of mechanical equipment, and it can be that could be an efficient option if the site is open and the mechanical equipment is available. Once the trench is open, we're typically sampling one or more vertical increments up the sidewall of each depth interval in as near a core shape sample as we can. So in this illustration, there are two vertical layers targeted in this trench. So again, in these are two different vertical decision units, and in each of these we would collect increments along the sidewall at the predetermined increment intervals, the number of increments you want to collect. And in this case, we typically always start at the bottom because we don't want to start here and have the soil fall down and potentially cross-contaminate the bottom interval. So we'd sample this bottom interval first and then go up and take the top interval sampling. Another approach is that you could actually use coring devices to sample a top layer down to a certain depth, and then as that depth lift is taken out, then come back with your coring device and sample the next lift, and after that's removed, sample down. That's another technique that could be used. I should mention that trenching equipment has also been used effectively in larger DUs where multiple soil depths are being accessed, and can be a good alternate to, say, using a push rig. In that case, a trench is dug to the appropriate depth along each of the planned increment rows in a DU. Then the increments collected at systematic random locations from the trenches along the sidewalls in a core shape. Subsurface decision units, where we're typically utilizing drill rigs, especially for larger and deeper subsurface investigations, increases cost and complexity of the work. That's true in any subsurface type investigations. In addition, because the drill cores are generally relatively large in diameter, 2 to 3 inches, and the DU depth intervals of interest can be several feet or more in depth, MIS, or multi-increment subsamples, must be collected from the larger mass of the core, which increases time in the field for this field processing of your samples. Also, if VOCs are targeted in the subsurface investigations, this presents additional challenge that must be well planned for, to collect multi-increment samples from the cores into methanol, and to closely coordinate the timing of core extraction and core opening by the driller in order to limit the time the core is on the surface and open before subsampling, to prevent the loss of VOCs. Here's a track-mounted drill rig working to collect cores on a site. Like other DUMIS investigation, the desired goal is to utilize a minimum of 30 cores in each subsurface DU for characterization, and then you'll have a given number of vertical decision units depending on how deep you're going and how the length of your targeted depth intervals as you're going into the subsurface. This is one open core with 3 targeted DU depth layers for a subsurface investigation, and each layer is subsampled separately and subsamples placed in their respective DU sample container. In this case, these are being sampled for non-volatile contaminants. From each layer here, these are subsampled and then put in the collection bag for DU layer 1. This is subsample put in DU layer 2 and DU layer 3. Then the next of the 30 or more cores are brought up. Those same layers are exposed and subsampled, and each respective layer is put in their respective sample containers to make up the bulk multi-increment sample that will be sent to the lab. Combining the full 30 cores from each subsurface DU layer typically results in much larger combined increment mass for each DU layer than a lab could handle. So, as I mentioned, field subsampling is commonly necessary to prepare MIS samples to send to the lab. Subsampling subsurface cores for non-volatile contaminants is generally not as complex as subsampling for VOCs. For a non-volatile contaminant investigation, cutting a small wedge along the entire core length of the DU layer may be a good and fast option. However, if the soil in the core is rocky or very loose, regular spaced subsample plugs, like using a 5 to 10 gram plastic coring device every 2 to 6 inches down the length of the core of the DU layer depth, may be the preferred method to subsample each core. In this case, the multiple subsample plugs from the length of the specific DU layer represents one increment for that DU layer. If you're targeting volatile contaminants, the regularly spaced small plug approach is selected to limit disturbance and exposure and minimize VOC losses. The subsampling plugs collected from 2 to 6 inch intervals along the whatever the length of your DU layer core is would be combined into a container of methanol large enough to hold the additional subsampling plugs from all other cores collected from that same DU layer depth. When coordinating VOC sampling, it is also critical to ensure that you work closely with the driller so each core brought to the surface can be opened and subsampled by the sampling team in as short time as possible. Again, we're trying to minimize potential loss of VOC, so you want those cores processed as soon as they're brought to the surface and opened up. This slide illustrates sampling a core for non-volatile contaminants along the length of the core. In this case, this entire core was the depth of interest, and they're taking a utility knife-like tool in this case, and the soil was holding together well for that, and slicing a core, which is illustrated by this yellow core out of here, slicing a wedge out of the entire core length, and that becomes the subsample for this core. again, we're attempting to reduce the overall mass of each core that goes into the multi-increment sampling, so you can send that to the lab and they can have a mass that they can work with and process. Again, whenever you're subsampling, have to subsample in the field, you'll also want to take replicates of your subsampling process. So these are different than the field replicates, which would be additional systematic randomly located cores throughout a specific DU. These are replicates of your subsample of the core. So if we wanted to do replicates on this core, we would take another wedge perhaps on this side of the core and another wedge on the opposite side of the core. So you'd have triplicate samples or 3 different wedges out of the same core. And again, we'd compare analysis results to ensure that the data from the 3 cores matched appropriately, were appropriately precise, so that you know that your subsampling method for the cores was representative. This illustrates subsampling the cores with the small plastic open-ended coring device. These are typically 5 to 10 grams, and as I mentioned before, you would take these plugs at various intervals along the length of your DU layer to attempt to get a representative sample of the contaminants that's along the entire core. Typically that's anywhere from every 2 inches to every 6 inches, depending on the degree of heterogeneity you might expect of the contaminants in those cores. So when you're doing these subsurface investigations for drill rigs, there's an obvious increased cost and effort to collect the subsurface samples, and in some cases, field triplicate samples may not be feasible due to timing issues or cost issues that come up. So if you're doing triplicate cores for your subsurface layers, that would be 90 cores in the DU versus 30 cores, and that would be done in 10% of the DUs you're investigating. So in the case that 90 cores triplicate samples could not be collected due to some limitation, then in that case we'd encourage at least the collection of field duplicates versus triplicates, and that would be 60 cores in a DU versus 30 cores to help evaluate the precision of the effort. Replicate sampling is really the only way that you can evaluate how precise the sampling effort was, because contaminant heterogeneity can vary tremendously at different sites for different chemicals, etc. So we always collect replicates so we can better defend the data, and they're important in every investigation. In spite of that, we do come by situations where, for one reason or another, the inadequate number of field replicates or the ideal number of field replicates cannot be collected for some reason. In that case, you do the best you can, and it's very important then to note the limitations of the data collection in any sampling reports, and to consider those limitations when making final site decisions. It may drive more conservative final site decisions, obviously, if you don't have any replicates to know just how precise your data was. This slide is illustrating the lab subsampling process, and as we mentioned earlier, it's very important that the lab is following up appropriately with your MIS sample, because you don't want the lab to negate all that work you've done in the field collecting your multi-increment sample by just opening up your large bag and taking a little hit off the top of that bag and analyzing that, because they would not be getting a representative sample of what was in that large bulk sample. So again, the procedure in the lab would be to initially dry the samples. So they're dried on large racks. Typically the labs that are processing these samples are establishing dirty areas, or certainly much dirtier areas than their instrumentation rooms. They're usually in separate rooms, separate ventilation. They're spreading out the multi-increment samples across large trays, usually on racks, and drying them, air drying them before analysis. All our sample analysis need to be reported on a dry weight basis. So for non-volatiles anyway, a good way of accomplish that during processing is simply to air dry them before they're subsampled for lab analysis. These samples are air dried typically anywhere from overnight to a couple days, depending on how wet the samples are. And periodically the labs will go into the sample and weigh portions, or weigh the entire sample, determine that it's reached dryness and is not losing weight with additional drying time. Once the sample is air dried, the entire bulk sample is then sieved to a known particle size. As we mentioned earlier, we typically sample or sieve all samples to the less than 2 millimeter particle size, which we define as soil particle size. And once that's done, we have a known particle size. The maximum particle size in our samples are less than 2 millimeter. And once you know the maximum particle size in your samples, you can then determine the minimum subsampling mass that's needed by the lab in order to reduce fundamental error in the lab to a reasonable level. So any sample you send to a lab, the lab should be asking you how you want that subsampled, and it's all based on the particle size. So if you don't sieve the sample, you don't know what the particle size is, so you're shooting in the dark. You don't know exactly what mass to analyze in order to reduce that fundamental error in the lab. So that's an important feature. Also, be aware that now in most cases a 2 millimeter particle size is just sorting out those sticks and stones. It's a pretty large particle size. But be aware, if you're interested in something larger than 2 millimeters, that's going to be a special case, and you want to make sure that they save that material from the greater 2 millimeter. A good example might be if you're looking at in situations where there's large particles like lead pellets or something like that. You certainly want to know what lead pellets were in that larger sample, so you'd want to, in that case, you'd want them to save all the pellets that were in the larger fraction, count them, weigh them, etc., so that you can consider that in your data and risk assessment for the site. Paint chips might be another example if they don't make it through the less than 2 millimeter sieve. So if you've got those situations on site, be sure and make a note of that, so that you're telling the lab what they need to do with that. Once the samples are sieved, the entire bulk sample has to be processed. Once that entire bulk sample is sieved through your 2 millimeter sieve, or in certain chemical specific cases, they might be sieving to even finer fractions, like for lead or bioaccessible arsenic. It's typical to look at perhaps in addition to the 2 millimeter fractions, smaller size fractions. In any case, once the sieving is done, that entire mass of the sieve sample is spread out again widely, typically no deeper than 1/4 inch deep across the tray, and then the lab to take their lab subsample, typically for less than 2 millimeter sample, it's always at a minimum of 10 gram samples, and they'll be doing just what you did in the field. Then they'll locating systematic random locations across that spread out thin soil, collecting those increments. They're using tools that are getting through the entire depth of that narrow depth increment. So typically, as you see in the lower photograph, square bottom tools, so they can reach to the bottom through that layer down to the bottom of the sampling tray to get the full depth of that layer at each one of the random increments. Obviously, these are very small increments because the total from all these increments are going to equal, say, 10, 30, 50 grams, something like that. So again, they'll choose their sample size to get their appropriate subsampling mass, their tool to get the appropriate mass. This tool here is simply a metal straw, and if some samples are very fine, ground very fine, you can actually use that like a coring device to put vertically into the fine grained soil and core it, and it'll stay up in. If you put your finger on the top, it'll stay in the core, and then you can release that and collect your cores that way with real ground or really fine grained samples. So that's the procedure of getting subsample, and then your replicates would be collected again from the entire bulk sample. They go back again to the entire bulk sample remaining after the first primary sample has been taken. Then they collect their subsampling replicate from separate systematic random locations throughout this spread out sample, and that would become your duplicate and or your triplicate in the lab to look at variation and how representative the lab subsampling data are to represent the entire bulk sample, the 1 to 2 kilograms that you sent them. I'd also note that it's common to see in lab protocols for soil samples now, lots of talks about they homogenize the sample before they analyze it. We don't use any of that lingo in our guidance, because homogenize can oftentimes mean they open up a jar and they stir around with a stirring rod or something like that, and then they take a hit off the top. All they're doing is increasing the heterogeneity of the contaminants in there, because typically when you stir something in a container, the fines will go to the bottom and the larger particles stay to the top. So it's very important that you get away from this idea of homogenization. The way you collect a representative subsample is to spread it out thinly and collect these systematic stratified random locations throughout the depth of your layer in the entire bulk sample. That's how you're getting representative samples, nothing to do with homogenization. So I've mentioned earlier most of these points about when you're looking at volatiles that we're generally using methanol, so you're putting roughly equal weights of methanol for the per gram of soil you're putting into that jar, and it's very essential that you coordinate closely, of course, with the lab, because the lab has to provide an adequate amount of methanol, usually fairly large volumes, to accommodate the multi-increment samples from numerous cores that are going to go into that multi-increment sample in methanol. Here's an illustration of the larger containers. You'll notice these are narrow mouthed to reduce any potential evaporation or loss of methanol. Typically when you're inserting your increments, usually these small plugs, you got to make sure they fit into the mouth so you can put them down in there. And usually we're opening and closing the lid again to reduce potential loss of the solvent during the procedure. Methanol is the preferred method for collecting MIS samples. Most labs consider that the gold standard amongst the options that are noted in method 5035. There are other allowable sample preservatives in that option, but we encourage the use of methanol whenever possible. Again, when the samples are put into the methanol, then the VOCs are immediately preserved there and captured, and that's what we recommend. This is just a photo illustrating the setup, the carefully controlled setup for sampling VOCs from cores. And here's two workers working on a core, taking each one is taking separate random locations across the core to do replicates from this core and placing them in bottles of methanol here. So again, I've mentioned very important to coordinate with the driller, so the driller isn't stacking up dozens of cores sitting out in the sun before they're opened up and you get to them to subsample. You want to have the cores come out of the ground when your samplers are ready to process that core as soon as possible. You want to collect these cores, get them into the methanol as soon as possible. Another way to speed things up is to have multiple sample teams or tables working on multiple cores at one time. So there are alternates to consider if the methanol method in the field presents problems, and Hawaii is unique, perhaps unique in that we have work on all these different islands, and there are shipping regulations because methanol is a hazardous material that limits shipping certain amounts of methanol air shipment from island to island. So consequently, due to those shipping restrictions, some consultants have had to resort to collecting individual subsample cores or subsurface or cores from the subsurface in sealed or vapor sealed small sampling tubes like an Encore tube, 5 to 10 grams, and shipping these multiple cores all frozen to the lab. That the lab would then thaw them out and combine them in methanol in the lab. Working in a sediment environment, the same DUMIS sampling procedures are involved. You just have to select tools or use tools that are appropriate to use in the water and to obtain the sediment layer that is targeted here. So again, you would in the sediment environment in which you're targeting here, you would identify your 30 systematic random locations. You can have tapes and markers, flags along the sides of a narrow canal or something like this to help mark intervals, and so that someone wading the water can use those as guides to locate samples as they're going along. In this case, we're sampling in an industrial canal, looking at the 40-inch depth, and a homemade tool was used in this case, simply a aluminum rod, hollow aluminum rod that's affixed onto a PVC pipe so that it can be put vertically down into the sediment, and then you put a plug into the top of the core once it's in the sediment to help hold it in, pull it up, and collect the 4 to 8 inch increment is what we're shooting for here. And this is illustrating it was the core is pushed out with a dowel onto a paper plate here to show that in this case a good core was able to be obtained with this this homemade device. Here's an example of using a commercial coring device for soil sampling in a large estuary pond in the Hilo area. This is the commercial core. It's about 2.5 inches in diameter. Unfortunately, we weren't able to find a commercial core in a much smaller diameter, which would have been preferable for our use. But it had a valve in the top of it that once you pressed it into the soil and pulled it up, the valve would close to help vacuum-wise hold the sample in the coring tube as you're pulling it up out of the water. The platform we sampled out of was just a small skiff, a flat-bottom skiff that was reasonably stable. And you can see here in this case we're trying to pound down the core down further in the sediment so that we can obtain at least 12-inch cores out of each one of these cores. We set up different 5 or 6 decision units throughout this large estuary, about a 30-acre estuary, and collected 30 cores at systematic random locations throughout each DU. The increment locations in this case were located using a handheld GPS to locate the points in the water. After the cores were collected, you'll see they're all collected in the boat, brought up to this commercial device had a simple splitting device that you could attach onto the bottom, push the core up from the bottom, and then slice off the core at any specific interval you wanted to. In this case, we chose the layers of interest as 0 to 4 inch, 4 to 8 inch, 8 inch to 12 inch. The contaminant of interest in this case was arsenic. There was arsenic wastewater dumped into this pond for many years. Typically, with these commercial devices, this pond at high water was about 12 feet deep. So typically there are commercially coring devices that you can employ in waters easily up to about 15 to 20 feet deep. Once it gets deeper, then we're looking at different challenges and different tools, and obviously as you get deeper, it's potentially costlier, slower, more time consuming to collect cores in a given decision unit. We'd still be shooting or using the same principles applying to sediment in deeper water. Once the increments were collected out of this pond, as I said, the core diameter was quite large, 2 to 3 inch in diameters, so we couldn't just collect each 4-inch increment and combine those 30 increments and send that to the lab because the mass was much larger. This is about a 2-gallon bucket, and you can see how those samples were about 2 gallons, which was too large for our sample for our lab to process. So we spread the sample out very thinly and used, in this case, plastic paint scrapers to subsample systematically, randomly, in this case, kind of like in a checkerboard fashion throughout the depth of that interval. And we created 3 subsampling replicates out of each bulk sample here. And that got each subsample down to a gallon size that we could send to the lab for processing. Finally, I want to just quickly go over use of field screening device in the context of DU MIS investigations. Like EPA and other bodies, the Department of Health here in Hawaii supports the use of field screening devices to streamline or expedite site investigations. In our case, the common contaminants that we're looking at here, some of the most common contaminants are lead and arsenic, sometimes mercury, and we can use a field portable screening device, a field portable X-ray fluorescence or XRF device to screen for these metals. So there's been a number of cases where these have been put to good use in investigations that combine both the use of these field screening device and multi-increment sampling. The way that we prefer to collect samples for XRF measurements when we're going to a site and initially screening it for metals is to actually go out to your selected DUs, like you would go out and collect a surface soil sample, put it in a plastic bag, a large plastic bag so it can be spread out thinly, and then take your XRF readings through the plastic. You typically take these through a plastic bag anyway, and instead of just one discrete sample you might do if you were doing this in the field, then for this this multi-increment sample you've collected to represent the surface layer in your chosen DU, you can sample this a great number of times in the bag and average them to get what we think is a better representation of what might be in that decision unit. So we might take 10 to 20 XRF readings on this side of the bag, then flip it over, take another 10 to 20. These readings are recorded, and we can average those readings then, these 20 or more readings of the XRF, to come up with a screening value or a screening number for the metal of interest for that decision unit. And we found that these have been used to great effect in initial screening efforts, especially things like large surveys of looking for lead around water tanks, looking for lead, arsenic around building foundations where you may expect them, as an initial investigation just to see if there's any significant contamination there. Then if you get significant readings, you can come back then and use those readings and that data to lay out decision units and collect those for more precise confirmation sampling. Of course, we're assuming in all this that the operator is very familiar with the operation of their instrument and appropriate calibration is maintained. In some cases you want field-derived spiked standards to test, and we found that the more familiar the operator is with the instrument, of course, the more reliably they can be used and interpreted. This is an example you've seen before, and Roger mentioned it the other day, of where an XRF was used to take a fairly dense grid of sampling points, and each of these points, these were actually from a 1 meter area and 5-point readings from the XRF. So these are not just one discrete XRF reading from these locations, but a little bit more rigorous XRF determinations from each one of these points or averages. And from that data, you can definitely see where the heavily contaminated area of this site was. It's outlined here in red. And this was excellent. It provides good initial data, enough for you to use this data to start follow-up actions and planning for removal, planning for capping, whatever approach might be taken. However, there were some outlier points here. It's less clear of whether they're really representative. Probably not a big contamination here, but nonetheless, that's the hazard of using a discrete sampling method is that you'll get these artificial cold spots or hot spots, and you don't quite know how to interpret them. Consequently, we don't use the field instrument for the final decision making. So in this case, we would advocate the approach using the field screening device to focus in. These are our more highly contaminated areas, so we located smaller decision unit sizes here and would advocate sampling from these smaller decision unit sizes. First here with DUMIS procedures, and also an attempt to locate smaller here to get a more precise boundary between the areas that may be contaminated and maybe not. As you go further out, we would increase the size of the decision units here, perhaps to the lot sizes that are proposed for the future development, and test those with our DUMS for confirmation sampling before the final decisions or the final site clearance is given for the work on this site. By the way, this was arsenic contamination from a former pesticide mixing. The most concentrated areas, arsenic levels were over 10,000 part per million in soil in that area of the site. Last slide, this is just going over some of the common issues, or what we're calling here DUMIS investigation mistakes or problems that we've talked about. I just wanted to point out here, as you look down this list, you'll hopefully recognize points that we've made throughout these webinar series about these issues. And I wanted to note that within our technical guidance manual, there's a specific section I believe it's in section 4 that covers these common DUMIS investigation issues in more depth. So each one of these, there's more detail given, and it's a good way to take advantage of the experience we've had here in Hawaii on common pitfalls or issues that we see on a site that can be improved when you're attempting to apply DUMIS sampling approach on sites. Okay, thank you. Thank you very much. That's it.
Thanks, John. So questions that we received with this webinar and answers and notes are posted to the HEER webinar page. So refer to the HEER webinar page for details on that. Following after this slide are a series of slides on each of the common problems and mistakes that John just briefly discussed. See section 4 of the TGM for additional details on this. There's no audio associated with these slides. We'll spend a few seconds on each one and then move to the next ones.